Well, welcome back to our course, Networks and Distributed Systems, based on the textbook by Jim Carouse and Keith Ross, Computer Networking, a Top-Down Approach. So far we have had an introduction. We've talked about the application layer of the TCP/IP model, the transport layer of the TCP/IP model, and now we are into the network layer of the TCP/IP model. The network is responsible for addressing and routing, and to this point we have discussed addressing and forwarding to a pretty good extent. In the last lesson we had begun to evaluate the new IPv6 standard for a network datagram. We're going to continue with that discussion by talking about what it's going to take to migrate from IPv4 to IPv6. So let's get started. Now that we've seen the technical details of IPv6, let's consider a very practical issue. How will the public internet, which is based on IPv4, be transitioned to an IPv6? The problem is that while new IPv6 capable systems can be made backward compatible, that is, can send, route, and receive IPv4 datagrams, already deployed IPv4 capable systems are not capable of handling IPv6 datagrams. Several options are available. One option would be to declare a flag day, a given time and date when all internet machines would be turned off and upgraded from IPv4 to IPv6. The last major technology transition from using NCP to using TCP for reliable transport service occurred almost 25 years ago. The Network Control Program, NCP, provided the middle layers of the protocol stack running on host computers of the ARPANET, the predecessor of the modern Internet. NCP preceded the Transmission Control Protocol, TCP, as a transport layer product used during the early ARPANET period. NCP was a simplex protocol that utilized two port addresses, establishing two connections for two-way communication. We already talked about how TCP is full duplex. NCP was not. Even back then, when the internet was tiny and still being administered by a small number of quote-unquote wizards, it was realized that such a flag day was not possible. A flag day involving hundreds of millions of machines and millions of network administrators and users is even more unthinkable today. There are two approaches, which can be used either alone or together, for gradually integrating IPv6 hosts and routers into the IPv4 world, with the long-term goal, of course, of having all IPv4 machines eventually transition to IPv6. Probably the most straightforward way to introduce IPv6 compatible nodes is a dual stack approach, where IPv6 nodes also have a complete IPv4 implementation. Such a node, referred to as an IPv6/IPv4 node, can send and receive both IPv4 and IPv6 datagrams. When interoperating with an IPv4 node, an IPv6/IPv4 node can use IPv4 datagrams. When operating with an IPv6 node, it can speak IPv6. IPv6/IPv4 nodes must have both IPv6 and IPv4 addresses. They must also be able to determine when another node is IPv6 capable or IPv4 only. This problem can be solved using DNS, which can return an IPv6 address if the node name being resolved is IPv6 capable, or otherwise return an IPv4 address. Of course, if the node issuing the DNS request is only IPv4 capable, the DNS returns only an IPv4 address. In the dual stack approach, if either the sender or the receiver is only IPv4 capable, an IPv4 datagram must be used. As a result, it is possible that two IPv6 capable nodes can end up sending IPv4 datagrams to each other. In this slide we've got in front of us right now, suppose node A is IPv6 capable and wants to send an IP datagram to node F, which is also IPv6 capable. Nodes A and B can exchange the IPv6 datagram. However, node B must create an IPv4 datagram to send to C, because as you can see, node C is IPv4. The data field of the IPv6 datagram can be copied into the data field of the IPv4 datagram, and appropriate address mapping can be done. However, in performing the conversion from IPv6 to IPv4, there will be IPv6 specific fields in the IPv6 datagram. For example, that flow identifier that we were talking about, that have no counterpart in IPv4. The information in these fields will be lost. Therefore, even though E and F can exchange IPv6 datagrams, the arriving IP4 datagrams at E from D do not contain all the fields that were there in the original IPv6 datagram sent from A. The alternative to the dual stack approach is known as tunneling. Tunneling can solve the problem that we just talked about, allowing, for example, E to receive the IPv6 datagram originated by A. The basic idea behind tunneling is the following. Suppose the two IPv6 nodes, for example B and E, want to interoperate using IPv6 datagrams but are connected to each other by intervening IPv4 routers. We refer to the intervening set of IPv4 routers between the two IPv6 routers as a tunnel. With tunneling, the IPv6 node on the sending side of the tunnel, for example B, takes the entire IPv6 datagram and puts it in the data payload field as an IPv4 datagram. This IPv4 datagram is then addressed to the IPv6 node on the receiving side of the tunnel, for example E, and sent to the first node in the tunnel, C. The intervening IPv4 routers in the tunnel route this IPv4 datagram among themselves just as they would any other datagram, completely unaware that the IPv4 datagram itself contains a complete IPv6 datagram. The IPv6 node on the receiving side of the tunnel eventually receives the IPv4 datagram, determines that the IPv4 datagram contains an IPv6 datagram, extracts the IPv6 datagram, then routes that IPv6 datagram exactly as it would had it received the IPv6 datagram from a directly connected IPv6 neighbor. That's not confusing, is it? There you see it. Just out of curiosity, what is the difference between that IPv6 datagram that has been put inside that data field? What is the difference between that one and then another one that is just the data itself without that other IPv6 related information? What's the difference? Think about that. One important lesson that we can learn from the IPv6 experience is that it is enormously difficult to change network layer protocols. Since the early 1990s, numerous new network layer protocols have been trumpeted as the next major revolution for internet. But most of these protocols have had limited penetration to this point. Introducing new protocols is difficult to do. On the other hand, the internet has witnessed rapid deployment of new protocols at the application layer. Classic examples, of course, are the web itself, World Wide Web, instant messaging, P2P file sharing. Other examples include audio and video streaming and distributed games. Introducing new application layer protocols is relatively easy to do. In summary, in the future we can expect to see changes in the Internet's network layer, but these changes will likely occur on a time scale that is much slower than the changes that will occur at the application layer. Well, that finishes our discussion of IPv6 and the conversion from IPv4 to IPv6. We're about to move on to other topics within the network layer, but so why don't we just take this opportunity for a break right now before we start something new. Go on out, study your notes, update your study guide, and when you're ready, come on back and we'll continue.